Black holes are real. That part we've confirmed. But everything we thought was happening inside one, the crushing singularity, the infinite density, the point where physics breaks, that picture is almost certainly wrong. And the evidence for that isn't coming from fringe theorists or speculative philosophy. It's coming from the same physicists who spent decades defending the old model. Here's what's so strange about black holes. The closer science gets to them, the more the inside of one becomes a problem, not a mystery waiting to be solved, an actual contradiction built into the math. There's a number at the center of all of this. We'll come back to it because that number is the reason everything we thought we knew about singularities doesn't hold. Let's start with what we actually know. In 1915, Albert Einstein published his general theory of relativity. It rewrote the rules of gravity entirely. Instead of thinking of gravity as a force, Einstein described it as a curvature of space and time. Mass bends space-time, and other masses follow those curves. Within a year, a German physicist named Karl Schwarzschild solved Einstein's equations while serving on the Eastern Front during World War I. He found something Einstein hadn't expected. The math predicted that if enough mass got compressed into a small enough region, space-time would curve so sharply that nothing, not even light, could escape. Einstein didn't like it. He wrote a paper in 1939 arguing that such objects couldn't actually form in nature. He thought the math was pointing to something physically impossible, a pathological solution to a beautiful equation. He was wrong. They do form. We've seen them. For decades after Schwarzschild's work, the idea sat in the background of theoretical physics as a curiosity. Then, in the 1960s and 1970s, two things happened that forced the field to take it seriously. First, astronomers began detecting quasars, extraordinarily luminous objects at the centers of distant galaxies, outputting more energy than entire star systems. The only mechanism that could explain that output was a massive, compact object consuming surrounding matter at enormous rates. Second, Roger Penrose published a landmark paper in 1965 proving that under Einstein's own equations, a collapsing star doesn't just stop, it collapses all the way down. Given the right conditions, the collapse doesn't bottom out. It continues indefinitely, compressing matter to a single point of infinite density. That point became known as the singularity, and for a long time, physicists treated it as real, not metaphorical, not a placeholder, a literal, physical location inside a black hole where density becomes infinite and the known laws of physics simply stop applying. Here's the problem. Infinity in physics is almost always a warning sign. When your equations produce infinity as an answer, that usually doesn't mean reality is infinite. It means your equations have broken down. They've hit the edge of their own validity. Think of it this way. Classical physics predicted that a hot object should radiate infinite energy at high frequencies. This was called the ultraviolet catastrophe. The answer the math gave was clearly wrong. That contradiction pushed physicists toward quantum mechanics. The infinity wasn't a feature of the universe. It was a signal that the model was incomplete. The singularity, many physicists now argue, is the same kind of signal. Einstein's general relativity is one of the most tested and confirmed theories in the history of science. But it doesn't include quantum mechanics. And quantum mechanics is the framework that governs the behavior of matter at extremely small scales. A singularity is, by definition, an extremely small scale, the smallest possible scale. So, you're applying a theory that explicitly ignores quantum behavior to the regime where quantum behavior is most dominant. that's not a minor oversight. That's applying the wrong tool to the most extreme situation in the universe. So, what actually happens at the center of a black hole? The honest answer from most physicists today is, we don't know. But we can say with increasing confidence what probably doesn't happen. Infinite density almost certainly doesn't happen. A true singularity, where all the math collapses and space and time cease to have meaning, probably isn't physically real. What might replace it is where things get genuinely interesting. One of the leading candidates is a structure called a Planck star. The name comes from the Planck length, which is the smallest scale at which our current understanding of physics can even define space. It's roughly 10 to the power of -35 meters, so small that it makes an atomic nucleus look like a solar system by comparison. The proposal, developed by physicist Carlo Rovelli and his collaborators, goes like this. As matter collapses inside a black hole, it doesn't compress to a point of infinite density. Instead, quantum effects kick in at the Planck scale and generate an outward pressure that halts the collapse. The matter bounces. And here's the part that makes this more than just a theoretical curiosity. If matter bounces at the Planck scale, it doesn't just sit there, it expands again. The core of the black hole undergoes a kind of quantum bounce, a rapid collapse followed by a rapid re-expansion. From inside the black hole, that re-expansion might happen relatively quickly. But because of the extreme time dilation near the singularity region, that quick bounce from the inside could look almost infinitely slow from the outside. We might be surrounded by old black holes that are right now slowly undergoing this bounce process. Their interiors expanding while their exteriors still look like perfect black holes from the outside. That's not science fiction. That's a peer-reviewed hypothesis from one of the most respected figures in loop quantum gravity. But the Planck star isn't the only challenger to the singularity picture. Let's talk about Stephen Hawking. Because Hawking's contribution to this story runs in two opposite directions at once, and that tension is exactly where the real physics lives. In the early 1970s, Hawking worked with Penrose to extend and generalize the singularity theorems. Together, they strengthened the mathematical case that singularities were unavoidable under general relativity. It was Hawking and Penrose who really cemented the idea that the center of a black hole had to be a singularity. And then Hawking spent much of the rest of his career undermining his own conclusion. In 1974, Hawking discovered something extraordinary. Black holes aren't entirely black. They radiate. When you apply quantum field theory to the space around the event horizon of a black hole, the math predicts that particle-antiparticle pairs are constantly flickering in and out of existence near the boundary. Occasionally, one particle falls in and one escapes. The escaping particle carries away a tiny amount of energy. The black hole very slowly loses mass. This is called Hawking radiation. It means black holes aren't permanent. Given enough time, an almost inconceivably long time, a black hole will eventually evaporate completely. Now here's where that creates a catastrophic problem for the singularity model. If a black hole evaporates, where does the information go? In quantum mechanics, information can't be destroyed. The state of a system, the precise description of every particle, every position, every momentum, has to be preserved somewhere. This isn't a preference or a convention. It's a mathematical requirement called unitarity, and it underlies all of quantum mechanics. But if a black hole forms from a collapsing star, all the information about that star falls in. If the information falls into a singularity, it's gone, crushed to a point of infinite density, removed from the universe. And then, if the black hole evaporates, the radiation it gives off is essentially random. It doesn't carry the information back out. You've started with a detailed quantum state, fed it into a black hole, and ended up with thermal noise, information destroyed. Hawking initially thought this was just something we'd have to accept. Maybe quantum mechanics was wrong about information conservation. Maybe black holes were the exception. But almost every quantum physicist pushed back hard. Destroying information would break the foundations of quantum theory. This became known as the information paradox. It's been one of the central open problems in theoretical physics for nearly 50 years, and here's why the information paradox is fatal for the singularity. If there's no singularity, if matter doesn't actually reach a point of infinite density and get removed from the universe, then the information paradox becomes much more manageable. The information might survive in the dense quantum core. It might escape gradually as the black hole evaporates. The books might balance. The singularity is what makes information destruction seem necessary. Remove the singularity, and you remove the information problem's sharpest edge. Hawking himself, near the end of his life, came around to this view. In 2016, he co-authored a paper with Malcolm Perry and Andrew Strominger, arguing that information might be encoded on the surface of the event horizon, not lost at the center. The idea drew on something called soft hair, a kind of quantum imprint left on the horizon by anything that falls in. It wasn't a complete solution, but it was Hawking signaling that the old picture, singularity at the center, information destroyed, was probably not right. Now let's talk about the event horizon itself for a moment, because there's a different kind of problem brewing there too. The event horizon is the boundary of a black hole. Once you cross it, you can't get back out. But in classical general relativity, it's a smooth, calm boundary. If you fell across it, you might not even notice. The space-time at the horizon of a large enough black hole is locally flat. There's no wall, no surface, no signal that you've crossed the point of no return. A group of physicists, Ahmed Almhayri, Donald Marolf, Joseph Polchinski, and James Sully, published a paper in 2012 that challenged this picture directly. It became known as the firewall paradox. Their argument went like this: if information truly escapes from a black hole through Hawking radiation, then the outgoing radiation has to be entangled with the matter that fell in. But quantum mechanics has a rule called the monogamy of entanglement. A particle can only be maximally entangled with one other system at a time. If the outgoing radiation is entangled with old radiation, it can't also be smoothly entangled with the interior. Something has to give. Either information is lost, or the smooth horizon is an illusion, or quantum mechanics needs to be modified. Their proposed resolution was dramatic. Maybe the event horizon isn't smooth and calm. Maybe it's a wall of high-energy radiation, a firewall that destroys anything that tries to cross it. If the firewall is real, there's no peaceful interior. There's no singularity at the center, because nothing survives to reach it. The infalling observer gets incinerated at the boundary. This would be a radical violation of general relativity, which explicitly predicts that the horizon is unremarkable in a local sense. So now you have at least 3 competing pictures of what happens inside a black hole. The classical singularity, the quantum bounce, and Planck star. and the firewall that erases the interior entirely. None of them is confirmed. All of them agree on one thing. The singularity as originally described, infinite density, infinite curvature, total breakdown of physics, is almost certainly not the right answer. Come back to your own body for a moment. You're sitting or standing somewhere on the surface of a planet, orbiting a star in the outer arm of a galaxy. Near the center of that galaxy, roughly 26,000 light-years away, sits a black hole called Sagittarius A star. It has a mass of about 4 million times our Sun. It's been there for billions of years, and at this moment, whatever is happening in its interior is completely inaccessible to us, not just because of the distance, but because of what the event horizon means. No information from inside can reach us. That is the hardest scientific fact here. We have detected the black hole. The Event Horizon Telescope captured its shadow in 2019 and published the image in 2022. The object is real, the boundary is real, the gravitational effects are real and precisely measured. But the inside is, in a deep technical sense, causally disconnected from our universe. We can't observe it directly. Every model of the interior is inference and mathematics. That doesn't mean the question is unanswerable. It means the answer has to come from a theory that unifies general relativity with quantum mechanics, what physicists call a theory of quantum gravity. We don't have that theory. We have candidates. String theory has proposed that black holes are actually described by a vast number of quantum states called microstates, and that the apparent singularity is a consequence of looking at an average rather than the precise quantum description. The work of Andrew Strominger and Kumran Vafa in 1996 showed that string theory could correctly count the number of microstates of a specific type of black hole, reproducing the formula Hawking had derived for black hole entropy. That was a major success. But string theory hasn't yet told us concretely what replaces the singularity. Loop quantum gravity, Rovelli's framework, predicts the Planck star bounce. But loop quantum gravity hasn't been confirmed experimentally either. Both are attempts at the same target. Neither has landed the decisive blow. And there's one more layer to this that doesn't get enough attention. Even the event horizon itself may not be as cleanly defined as we once thought. In classical general relativity, the event horizon is an absolute boundary. You can define its location precisely. But it turns out that this clean definition requires knowing the entire future history of the space-time. You have to know what will happen to the black hole forever, into the future, to know where the horizon is right now. For a black hole that will eventually evaporate, which Hawking radiation tells us it will, the event horizon starts shrinking before you'd naively expect. The horizon is a global structure, not a local one. This means the sharp line between inside and outside that sits at the foundation of the singularity picture is itself an approximation. It's an idealization that holds perfectly in a universe where black holes live forever. In our actual universe, where they evaporate, the geometry is murkier. The singularity sits inside an event horizon, inside a framework that was already idealizing the reality. You started with a mathematical solution to Einstein's equations. That solution produced a singularity, but the math was already assuming things: eternal black holes, no quantum effects, perfect symmetry that the real universe doesn't provide. The singularity was never a discovery about the universe. It was a discovery about the limits of the equations. What we know now, something is at the center of a black hole. Enormous amounts of mass are there. Space-time is curved beyond anything else in the observable universe. The gravitational effects on surrounding matter are real and measured. What we don't know, what form that matter takes at the center, whether space and time retain their meaning there, whether a quantum bounce occurs, whether there's a firewall, whether the information survives. What we can say, infinite density almost certainly doesn't happen. The singularity, as a literal physical object, is almost certainly a mathematical artifact, a signal that our equations have reached the edge of their own validity, not a description of something real. The granite in the equations that shouldn't be there, the density that doesn't match any physical process, the information that vanishes without a trace. These aren't proofs that the universe is broken. They're coordinates pointing to exactly where our map ends. The black hole is real. The event horizon is real. The gravitational power is real, measured, confirmed, imaged. But the singularity, the infinite, crushing, physics-ending point at the center, was never a fact. It was always a flag marking the place where we need better physics. And we're getting closer to that physics every year. Thanks for watching, and I'll see you in the next one.